let me tell you about parse trees. Okay, parse trees are a very useful way of representing a string in a context-free grammar that allows us to extract the meaning of the string. Okay, so let's see how that works in a few examples. So parse trees. Okay. And let's consider a very simple context-free grammar. So we have our start variable s, and it can transition to pound. Think of pound as a punctuation character, or 0s1. So you get strings of zeros followed by strings of ones, and in between a pound character. So let's see an example derivation. We start with our string s, our start variable s. It can transition to 0s1, 0s1. I'll take this s and make it another 0s1. So I get 0, 0s11, and I make it another 0s1. So I get 0, 0, 0s1, 1, 1. And now I can make this s into a pound. So I get 0, 0, 0, pound, 1, 1, 1. Okay. Now, so this is a string. This is a string. This is the derivation. This is a derivation. And now I'm going to show you what the parse tree looks like. Okay, so the way we construct the parse tree is we start from the first start variable, s, okay, and it transitions to 0, s1. So think of these as 3 children. So 3 characters in the string. We represent them as 3 children, maintaining the order. So this becomes 0, s1. Okay, so they become children of my root start variable. Now this variable s, this guy, okay, becomes 0s1. So this also has children, 0s1. Okay, and then this s also has children. This s becomes 0s1. So it becomes 0s1. Okay. Now these zeros and these ones never change. Okay, and then this s also has a child, but in this case it doesn't become 0s1. This s just has one child, which is the pound. So this guy transitions to pound. Okay. Now that is what we call the parse tree of this string. Okay, and it represents the string, not only the string but also the derivation. And actually, if I'm going to draw it in a slightly different way, and we'll see the structure of the derivation coming out in the parse tree. Okay, so let's draw it in another way. So I have s. Okay, then I have red s, okay, just to distinguish these s's. Then I have green s, okay, and then I have blue s. Okay, so then I have blue s, okay, and this s produced 0, s, and 1. So it produced the 0, a 1, okay, and this s. Okay, then this red s produced 0, produced 1, and the green s. Okay. And then the green s produced 0, produced 1, okay, and then the blue s. And then the blue s, what did the blue s do? It just produced pound. Okay. And what's nice about sort of this parse tree is that you can look at the subtree of any particular variable, and that shows you the string that was derived by that variable. So let's take, for example, the green variable, green. We look at the subtree under green. So the subtree under green is this guy, and that's the string that was produced by s, by the green s. And for example, here's the string that was produced by the red s. Okay? And so the parse tree sort of, shows in very clear detail which substrings in the full string were derived from which variables in the derivation. Okay, let's take a slightly more complicated example. Okay, to show you what I mean by the parse tree reveals the meaning of the string. Okay, and this is also going to illustrate a context-free grammar for arithmetic. So, okay, here's a slightly more complicated example. So, a grammar for arithmetic, baby arithmetic. Okay, so your start variable can go to either the start variable plus the start variable, or the start variable times the start variable, or in parentheses the start variable, or just 2. So this is a grammar for arithmetic expressions, okay, that involve just 2. Okay, and let's consider a string, and it turns out that this string can be derived. So consider the following string: 2 plus 2 times 2. Now, okay, if you were, in 5th grade and you were asked evaluate this, you'll see that there's some ambiguity. Should I do 2 plus 2 first and then multiply by 2, or 2 times 2 first and then add 2? So this could either equal 2 plus 2 times 2. So 2 plus 2 is 4 times 2 is 8, or 2 plus 2 times 2, which is 2 plus 4, which is 6. Okay, And now when you grow up in high school, when you grow up in 5th grade and 6th grade and so on, you're told that multiplication takes precedence over addition. That's to avoid this ambiguity. And it says that, this is the correct interpretation, the correct meaning of this string. But let me show you that when we look at parse trees, okay, and parse trees of derivations, that both of these meanings can be possible. So let's derive this string. So the first derivation will start with my start variable, and then it becomes s plus s. Okay, so that's this plus, and then it becomes s plus s times s. So I change this s into s times s. Okay, and now I'll use the notation can be derived. So there's some derivation where I replace each of these s's by 2's, one by one. I don't want to go through all those steps individually. So I'll use the producers with a star. There's some derivation that produces 2 plus 2 times 2. Okay, let me show you another derivation. And you might think, oh, well, aren't all derivations equivalent? So here's another derivation. I'll start, instead of starting by replacing s with plus, I'll replace s with times. So s goes to s times s. Okay, now, so here I started with plus and then replaced the second s. Here I started with times. I'm going to replace the first s with plus. S plus s times s. Okay, so this guy became s plus s, and now we can, produce all 2's for the s's. So we can produce 2 plus 2 times 2. Okay, so same string, different derivations. Now, in what sense are they different? Let's look at the parse trees. So the parse trees for this derivation start with s. Okay, then we have children s plus s. Okay, and then this s breaks up into s times s. Okay, and then they all become 2's. 2, 2, 2. Let's look at the parse tree for that derivation. Okay, so we have s breaks up into s times s. So its children are s times s. Then this is the guy that gets replaced with s plus s. Okay, and then we replace all the s's with 2's. 2, 2, 2. So we get 2 plus 2 times 2. 2 plus 2 times 2. Okay. Now, to show you what we mean by what you should sort of take as the meaning. So now, when we have an arithmetic expression, we have a parse tree, and we do something with the parse tree, and what's called post-order traversal. So if you don't know what that means, don't worry about it. Okay. But the way we evaluate parse trees for arithmetic expressions is using what's called post-order traversal. So what that means is that you start from the bottom. Okay. So here's the bottom, and you'll first do 2 times 2. So you'll do 2 times 2, 2 times 2, and then you'll go up. Okay, so this is 4. Then you go up, and this guy becomes 4, and this guy becomes 2, and so then this becomes 2 plus 4, which is 6. Okay, and then 4 plus 2, which gives you 6. Okay, so if you do post-order traversal, which is what we mean by the meaning of this parse tree, you will get the value 6. So if you evaluate this parse tree with post-order traversal. Let's see what happens if you evaluate this parse tree with post-order traversal. You can think of post-order traversal as extracting the meaning. So the meaning of this parse tree is 6. Okay. Evaluate the arithmetic expression. The meaning of this parse tree is you start at the bottom, so 2 plus 2. So 2 plus 2 gives me 4. And then I get 4 here times 2 times this 2 gives me 8. 4 times 2 gives me 8. So you see, the ambiguity that we had from the beginning is represented by 2 separate derivations, which have 2 different parse trees. And when I extract the meaning of the 2 parse trees, I get different results. I get different meanings. That's bad. So we say that this is an ambiguous grammar. So this is an example of an ambiguous grammar. And this is just to show you how parse trees can represent strings in a way that we can extract meaning. Okay? And ambiguous grammars are bad because we don't want to not know the meaning of a string. Okay? So we need to be able to uniquely evaluate, for example, arithmetic expressions. Okay? And it's possible to convert this context-free grammar into one that's not ambiguous, where all strings have unique parse trees, and so therefore unique meanings. Okay? But you can see the importance of having unique parse trees in a context-free grammar for any string. So imagine a web page. So you have a web page, that's a string. Now I construct its parse tree and then extract the meaning of that web page. I need to understand, what should I render? Well, it should be unambiguous what I should render. Or you have a program, which is a string. of characters. And I extract the parse tree for that program using the C++ context grammar, and now I have this parse tree, and now I extract the meaning. That should be unique, because that meaning of your program is what the computer should do with it, how the computer should process instructions. Okay? So when we construct grammars, we really like the parse trees to be unique so that the meanings of strings are well defined. HTML, C++ code, arithmetic expressions, and the list goes on. Okay. So, parse trees and how parse trees are used in context with an algorithm to extract meaning, like post-order traversal of arithmetic expressions. Okay, so just the dizzying array of possibilities when we are talking about context-free grammars for generating strings and representing the derivations as parse trees and so on and so forth. So you can read more about it in the text. I want to move on and talk about some of the limitations of context-free grammars.